Okay, earlier we have shown that this integral is going to be 0 when alpha I equals to alpha j, and it's going to be some constant. It's going to be 0 when alpha I is different from alpha j, and it's going to be some constant when alpha I equals to alpha j. So what we will do next is what is the value of this constant. So that's what we are going to find. So to this end, we will consider alpha I to be alpha j plus epsilon. Okay, what does that mean? That means we are considering alpha I to be in the neighborhood of alpha j. If you go back to the note, which I'm going to show you, which I'm going to try to show you here on the screen. Okay, so that's alpha j. So alpha I, I'm considering a small displacement from this alpha j by epsilon. Okay, so that's alpha I, which is at a distance of epsilon from alpha j. Okay, so this is on page 373, figure 1211. Okay, so epsilon is very much small. It's very small. That means alpha I is gonna be very close to alpha j. So when you square alpha I, which means you square alpha j plus epsilon, when you square that, you get alpha j squared plus epsilon squared plus 2 alpha j epsilon. Okay, but we said epsilon is much smaller than 1, so we can drop this term and we get that. So alpha I squared minus alpha j squared is going to be 2 alpha j epsilon. Okay, so we'll come back to use this later on. So I'm going to box it, right? Okay, and our goal is to find the result of this integral when alpha equals to alpha j. So I will take you back to equation 6. Okay. So this is where we are going to start. So we are going to consider each of these integrals when alpha I equals to alpha j plus epsilon. So when alpha I is going to be alpha j plus epsilon, and here alpha I is going to be alpha j plus epsilon. Okay, so in the limits as epsilon goes to 0, then we would be able to find, so again also here that's going to be alpha j plus epsilon. Okay, all right. So what would be the form of this integral? What would be the form of this integral? We already know what to substitute for this. Okay, we already know that, which I showed you earlier. So now let's look at these two integrals. First, if we look at this integral using integration by parts, we have shown it to be that so alpha j doesn't change. What changes is alpha I. It becomes alpha j plus epsilon. So since we are evaluating this at x equals to 0 and x equals to 1, at x equals to 0, because of that, still we get 0. At x equals to 1, this becomes jp alpha j, jp of alpha j, which is the zeros of the Bessel function. So this term still is going to be 0. Okay, so what we would have is going to be this expression with alpha I replaced by alpha j plus epsilon. Okay, so that's what we have in here. So this is what you get for alpha I equals to alpha j plus epsilon. Okay, now the second integral, for the second integral on the other hand, you cannot set, okay, let me take you back here. For the second integral, since here we are replacing alpha I by alpha j plus epsilon, and same thing here, alpha j plus epsilon, and we cannot say that this is equals to 0. Okay, so instead this is not going to be 0 because we don't know the behavior of jp of x. Well, actually we do know from the graph that I showed you. When you evaluate it at x, okay, I think let me show you here. All right, so this is what we should have. Okay, so this is what we'll have for the second integral. So this term is there, it's not 0, minus that. Okay, now when you evaluate this at x equals to 0, because of that, still it's going to be 0. Because of that, still it's going to be 0. But at x equals to 1, the upper limit, it won't be 0. So what we can write for this is going to be, follow me. So if you come back here, so that equation that I showed you there, it becomes like that. So you are going to evaluate this term only at x equals to 1. Okay? So only this part. Here I have substitute x equals to 1, so that's going to be jp of alpha j plus epsilon. As I showed you in the graph here, at this point, the function is not 0. At alpha j plus epsilon, the function is not 0. Okay, that's not 0. But at alpha j, it is 0. Okay, so because of that, this you have a non-zero value at x equals to 1, which is very important. So the rest is going to be the same. So this is the same. Now, what do we get then for please okay, all right, so now let's substitute the result that I just showed you there. So this integral minus that integral plus that, what do we get? So what we get here is, if you use the results that we have here and the results that we have here and the results that we have here, so this integral minus this integral plus the additional term, this is what you get. Okay, so this is what we get. Okay, oh boy. Oh man, technology. Okay, so this is what we get when we substitute those equations. So you have that, and I can rewrite this in this form. So if you just move this to the other side here and divide it by 2 alpha j epsilon, so you have this equation, okay? Okay, so we want to simplify this equation, okay? This equation. So how do we do that? So for that, I'm going to take you back to the note here. So we need to apply a Taylor series expansion for this part of the function, okay? So for this part, for this, we make a Taylor series expansion about epsilon equals to 0. So if I take you back to the note here, so according to the Taylor series expansion, here, so for a function f that is depends on the variable epsilon, that's your Taylor series expansion, which is equation 1232. So if my function f of epsilon is jp alpha j epsilon, then the first term is going to be jp alpha j plus epsilon evaluated at epsilon equals to 0. So that's going to be just jp of alpha. Okay, well, this should be alpha j. And the second one is you differentiate this with respect to epsilon and you set epsilon equals to 0. Okay, so when you apply this equation, what you find is this. Okay, please follow me. Okay, so this is what you'd find, okay? So the Taylor series expansion for jp of alpha j plus epsilon at epsilon equals to 0. Now, just what can you say about that, okay? So this one, so that's the Bessel function evaluated at alpha j. Remember, alpha j is the zeros of the Bessel function, so this is going to be 0. So the first term is going to be 0, and you would have only this term, that, and so on. So if follow me here, so since the first term is 0, that's what you get, okay? So we get this one. All right? Now, so I have got the Taylor series expansion for this function, okay? Now, what does this mean? So let's simplify this one. So if you simplify this one, that you can rewrite this as alpha j times d by dy jp of y evaluated at y equals to alpha j. So basically you can rewrite this as jp prime alpha j. So that means, you know, the derivative of jp with respect to y evaluated at y equals to alpha j. So that's obvious. So if I use this, and that, okay, into this equation, okay. So remember, here we have epsilon. So that epsilon kills this epsilon. Here I have alpha j. This alpha j kills alpha j. And what you would end up with is going to be that, okay. So therefore, this is what you would find, okay. So remember, our goal is to find the, let me take you back here. Our goal is to find the value is so our goal is to find the value of C when alpha I equals to alpha j. When alpha I equals to alpha j, what the value of C. So in order to find that, so I have to let epsilon goes to 0, okay. So in the limit epsilon goes to 0, then what's going to be the result of the expression that we found over there. So let's go back there, okay. So alpha I equals to alpha j means setting epsilon goes to 0. So as epsilon goes to 0, you see the higher order term starting from here, you know, the next term is going to be epsilon squared, the next one epsilon cubed, and so on. So all those terms are going to be 0, and only the first term would survive. So therefore, when alpha I equals to alpha j, what you would find is going to be this, okay. So that is the constant C that we are looking for. So therefore, the Bessel orthogonality relation can be written as, so alpha I alpha j x dx is going to be jp prime alpha I, which means that if the derivative of the Bessel function, first derivative evaluated at alpha I, first derivative of the Bessel function evaluated at alpha j, that's what the primes represent, okay. The primes means the first derivative times the canonical delta ij. So when I equals to j, so this I equals to j, so we get what we found over there. And when I different from j, this is going to be obviously because of the canonical delta, it's going to be 0, okay. So that is the orthogonality relation for the Bessel function. Yeah, so the Bessel functions are nasty functions. I don't like them. They are not friendly like the legendary polynomials or the associated legendary polynomials or the spherical harmonics. So I don't like them, so it's kind of messy, but we have found the orthogonality relation for this function, okay. So because of the 1 week we lost because of the extension of the spring break, so I'm gonna skip some topics related to the Bessel function. So I'm gonna leave that to you as a reading assignment. So the topic that I leave as a reading assignment to you is the asymptotic form of the Bessel functions. So that's on page 375. So the limiting or asymptotic forms of the Bessel function. So what do you get when x is much smaller than 1? And so those I will leave for you to as a reading assignment. You are gonna see this in quantum 2, where we study quantum scattering. So that's the only place that I saw application of the Bessel functions and the Bessel differential equation. So I will leave that as a reading assignment to you. And there is one example which I also leave it to you. So this example 1212, the lengthening pendulum. So so if you have a pendulum where the length is a function of time, or where the length changes with time, okay? So if you displace the pendulum and then release it, and you know what the pendulum that you know is the length of the pendulum is constant, but if this length changes with time, then in addition to the angular variable theta that depends on time t, the length is going to be also a function of time. So if you if you find the equation of motion for this mass using the Lagrangian, using the Euler-Lagrange equation, the differential equation that you end up with is going to be related to the Bessel differential equation. So in this example, you are asked to find the solution of the angular displacement theta as a function of the length L. Okay, so I will leave that to you. And also section 1212, the Fuchs theorem for second order differential equation. So I'm going to leave that one to you, including the example. Okay, and next time we will start partial differential equation. Okay, so that's the end of this chapter. So I have to skip this Fuchs theorem for second order differential equation and the example related to the Bessel functions and the Bessel differential equation. Okay, so that's going to be your reading assignment. I probably give you a homework assignments on Bessel functions. I haven't decided yet, but I will think about if it's worth giving you the homework assignment related to the Bessel function. You know, taking into consideration the time constraints that we have, it's probably not a good idea to give you homework assignment related to this section. But anyway, I will think about that. All right, thank you for your attention, and I'm gonna upload these videos that I recorded for this lecture on YouTube, and I create a link on the course website, okay, so that you would be able to access it. Okay. Anyway, all right. Thank you. Bye.